We're very happy to receive Edward Witten here today, and he'll be talking about no ensemble averaging below the black hole threshold. Thank you, Witten, for coming.
Thanks so much for the invitation. So the talk, as I've written here, is going to be based on this recent paper with Jean-Marc Schenker. And I'll begin by remembering the basic idea of holographic or ADS-CFT duality. So in ADS-CFT duality, you have a boundary theory in some dimension D. And the boundary theory is an ordinary theory, a normal QFT. Then there's a bulk theory in one dimension higher. That's a theory with gravity. The relation between them is that one lives on the boundary of the other. That's why it's called holographic. And the basic idea is that if you want to calculate the partition function of the boundary theory, you do that by summing or integrating exponential of minus the action over all choices of x. When I say all choices of x, I mean you pick the manifold x, you also pick all the fields in x, the metric on x, and everything else. And M comes with a conformal structure. And the metric on x has to agree in a certain sense with the conformal structure on M. So roughly speaking, the metric on x satisfies Dirichlet boundary conditions. Along the boundary of x, it agrees with the metric on M. And then under that rule, you calculate this partition function. There's one thing that's a little bit misleading about the way I described it, which is that M is infinitely far away. So M is not an ordinary boundary, but M is what's called a conformal boundary. I'm running out of space to write this, but M is a conformal boundary. It's at infinity in x, but in gravity with negative cosmological constant, it turns out that you can sensibly set boundary conditions at spatial infinity. So what's happening on what you specify on M, the metric or other fields on M, influence what happens on x. And the duality says that the partition function on M, and more generally, any observable on M, can be computed by summing over all choices of x in the interior. So I've kind of drawn this here. So here I've drawn M, which is the boundary of some x. And to compute something on x, you sum over all, to compute something on M, you sum over all possibilities on x. So you sum over all choices of the manifold x, of which I've drawn the simplest one topologically, just it looks like a disk or a ball. You sum over all choices of the manifold x and over all fields on x. Now, this works beautifully as long as the boundary M is connected. But as was observed in early days of the ADS-CFT correspondence, it's not so nice if the boundary is not connected. Here I've drawn a simple case where the boundary consists of two components, M and M prime. The bulk is connected, but the boundary isn't connected. So it looks, according to the rules I told you, that this is going to calculate the partition function on a disjoint union of two manifolds. But according to standard rules of ordinary quantum field theory, that's simply a product of two partition functions. This symbol here is for disjoint union. It just says that M and M prime are different Euclidean signature spaces, no points in common. And in ordinary quantum field theory, locality of quantum field theory basically tells you that the partition function of a disjoint union is just a product. So it looks like this connected manifold X with disconnected boundary is trying to calculate a connected correlation function between the two partition functions. So in other words, well, it's a contribution to Z of M times Z of M prime. But in some sense, intuitively, it's connected because the manifold X is connected. So it looks like it's computing a contribution to the product of two partition functions that we wouldn't get if we took it looks like it's computing a contribution to an expectation value of the product that we wouldn't get if we took the product of the expectations. Something a little bit like this makes sense in Lorentz signature, where quantum states can be entangled. But in Euclidean signature, the partition function is just a number. And likewise, any observable we would calculate in Euclidean signature, like a expectation value for product of operators, is just a number. So it seems that we're trying to compute a connected correlation function between numbers. So from a conventional point of view, this doesn't make any sense. In a given boundary CFT, the partition functions for given conformal structures on M or M prime are just numbers. So what would it mean to talk about a connected correlator? Maybe I'll stop here for questions, since I understand this is supposed to be like a journal club with a lot of discussion.
Yes, it is. Yeah, I didn't say this earlier, but if people, please feel free to ask anytime.
Okay. But if I don't get any questions, I won't insist. So I'll just go on.
Okay, I think that's fine.
So, well, this was the situation for a long time, I would say, since early days of ADS-CFT. A new perspective came a few years ago from JT gravity in 2 dimensions. JT gravity is a very simple model of 2-dimensional gravity, so simple you can solve it. So the action is just like this. Well, I'm going to assume negative cosmological constant, which I've chosen to be -2. And then the action is like this. And the classical equations are so simple you can completely solve them. Phi is a Lagrange multiplier that imposes the classical equation R equals -2. And then in 2 dimensions, that has a finite dimensional space of solutions on any given topology that's relatively well understood. And you could also solve the equation of motion for phi, although I haven't written it. So classically, this theory is simple enough you can easily analyze it. It's less obvious, but it's true that you can also analyze it quantum mechanically. But when this was done, the answer was surprising. As I just explained, this is a theory in 2 dimensions. So if you have gravity in 2 dimensions, the boundary is 1-dimensional. So the boundary system would be an ordinary quantum mechanical system. And you'd expect that you could completely specify a quantum mechanical system by giving us Hamiltonian H. The boundaries, assuming they're compact, are circles. And the most general metric on a circle has some circumference, is completely described as a flat metric of circumference beta for some beta. So we'd expect the partition function to be the trace of e to the minus beta h, or e to the minus beta prime h for m or m prime. And then you'd hope that if you calculate the partition function, you learn what's the h of the boundary dual theory. However, this problem was analyzed, and it turned out when you calculate the bulk path integral, which it turns out you can do completely, you find that the boundary theory does not have a definite h. To reproduce in the boundary the answers that you get from the bulk, you have to interpret the Hamiltonian h as being drawn from an ensemble of random matrices, rather than being a definite Hamiltonian. So if you average over a random ensemble of h's, the partition function then isn't a number, but a random variable. So it can have connected correlators. And Saad, Schenker, and Sanford described the ensemble of random matrices such that the connected correlators in that ensemble reproduce exactly what you get by the gravitational path integral with connected boundaries. Sorry, I said connected boundaries. I meant disconnected bulk, but disconnected boundaries. So the gravitational path integral in this picture precisely recovers what you get from the random matrix ensemble in this picture. Well, they found the random matrix ensemble that makes this true. Or better, I should say, they adapted work of Eynard and Arrington to do so. So this is a very compelling story. It's beautifully related to famous work of the Iranian fields medalist Maryam Mirzakhani on the volumes of moduli spaces of Riemann surfaces. So Mirzakhani's work had been related by Eynard and Orenton to a random matrix ensemble, and Saad, Schenker, and Stanford exploited the fact that that random matrix ensemble is the one that reproduces the bulk path integral of JT gravity. So this has suggested that possibly the resolution of the puzzle is the same in examples of the duality in D equal to or greater than 3, namely that the boundary dual of a gravitational system that participates in ADS-CFT duality is not a definite CFT, but an ensemble of CFTs that you're averaging over. However, I'm not aware that anyone has actually made that obvious proposal in print. I might be missing something, but I don't think I've seen it. If no one has suggested it in print, there's an obvious reason for that, which is that there's an obvious objection to this proposal. No suitable ensemble of boundary theories exists.
What do you mean here by suitable ensemble?
Well, I'm about to explain it in detail.
Okay.
Usually we're studying a theory that has some known symmetries. For example, we might have a 4-dimensional CFT that has n equals 4 supersymmetry. And then a suitable ensemble would be an ensemble of boundary theories that have the appropriate symmetries. So in that example, these would be theories with 4-dimensional n equals 4 supersymmetry. And we believe there are not too many of them. They're completely classified by the choice of a Lie group. And also there's a tau parameter, the coupling parameter. So that illustrates what I was about to say. In many much studied examples of the duality in dimension 3 or higher, in fact, in all the examples constructed, not all of them, sorry. Okay. In very, very many examples constructed from string/M theory, it's believed that all the parameters on which the boundary theory depends are known, and the bulk theory depends on all of the same parameters. I just mentioned in answer to Renan's question, the example of n equals 4 in 4 dimensions, but in the slides, the examples I give are different. Some of the original examples of the duality were ADS4 times S7, ADS7 times S4. In these examples, the only parameter is a single positive integer n. The only parameter consistent with the superconformal symmetry that these examples have. That's not a true theorem, but it's strongly believed to be the case. There are many other examples with more than one integer parameter, sometimes also finitely many real parameters. But the point is that in many cases, all parameters of the boundary theory are known, and the bulk theory depends on the same parameters. I maybe should have written consistent with its supersymmetry parameter algebra, and in some cases, other global symmetries, bosonic symmetries. But anyway, in many cases, all parameters of the boundary theory consistent with its symmetries are known, and the bulk theory depends on all of the same parameters. For example, for instance, in these examples here, the bulk theory depends on an integer n, but, sorry, I should have said the boundary theory depends on an integer n, but the bulk theory depends also on n, because, for example, n controls Newton's constant in bulk, or n can be measured as a flux integral on the sphere S7 or S4. So a bulk observer, in principle, could measure n, and once the value of n is known, the boundary theory is completely known. So there's no ensemble over which you could be averaging to reproduce that bulk theory. There's nothing you could be averaging over in an ensemble average. In this talk, we'll sharpen the puzzle by identifying a class of observables that are not subject to any apparent ensemble averaging. What I mean by that is that we'll describe observables that don't receive contributions in this situation, where the bulk is connected, but the boundary is not connected. So we'll find observables that look like they are just honest numbers rather than fluctuating. They're what we could call sub-threshold observables, where the threshold in question is the black hole threshold. Well, what does that mean? if you take n to infinity, or if you take Newton's constant to 0 from a bulk point of view, keeping fixed the excitation energy above the ground state, you see a spectrum of states that has a large n limit. These states are not black hole states, and our proposal is that their energies and spins and couplings are not subject to ensemble averaging. I put the word spins in parentheses because spins are discrete parameters. So the fact that they don't fluctuate is less striking. It's more interesting that the real valued parameters, the energies and couplings of the states, do not show any sign of fluctuations due to connected manifolds with disconnected boundary. So I claim that an observable that can be expressed just in terms of energies, spins, and couplings of states that are below the black hole threshold, states that are only a finite amount above the ground state, receive contributions only from manifolds with connected boundary. Another way to describe the observables that are not subject to ensemble averaging is that they're the ones that can be computed by integrability. So there are examples of ADS CFT duality that are integrable for large n. Not all examples, but some important examples, like ADS 5 times S5 is the most famous one. It's dual to n equals 4 on the boundary, on a 4 manifold. And so this example is integrable for large n. And integrability governs a lot of observables. But you can't learn about black holes by integrability. The observables that are governed by integrability are what I'm calling subthreshold observables. Integrability precisely accesses states and couplings below the black hole threshold. And somewhat related to that, there's localization. I didn't write it on the slides, but you can calculate a lot of observables by localization. Well, here I'm less certain of the answer, but I expect. Well, okay. Localization always gives a definite answer. It never gives something that fluctuates. So all observables computed by localization are
So
examples.
I have a question here. Sorry.
Let me finish my sentence though. All examples computed by localization are examples of observables that give definite numbers with no sign of fluctuation. Yes, go ahead.
So how do you see that integrability access these copies below the black hole threshold?
Well, it does in the following sense. I'll be a little bit more clear in a moment, perhaps, but if you take n to infinity, integrability is an expansion around n equals infinity. In the first instance, integrability is done at n equals infinity, but then you can expand around n equals infinity, although that isn't yet fully understood. But anyway, integrability lives near n equals infinity. And you study the states that have fixed energy or fixed dimension as n goes to infinity. Those are not black hole states. I probably will say this on the slides in a moment, but since you asked, I'll write it down now. So if you take fixed energy for n to infinity, that's below the black hole threshold. If you take the energy of order n squared for n to infinity, you get a black hole. Now, this scaling with n squared is for ADS 5 times S5. It's a different power of n in other examples, but the important thing is it's always a positive power of n. So to get to the black hole region, you have to take n large with the energy scaling as a positive power of n, where the power depends on the theory. To integrability studies what happens at fixed energy for n equals infinity. Is that clear?
Okay.
Okay.
Thank you.
Sure. So I know integrability studies things that are not black hole observables. Okay. It's more complicated for localization because some aspects of black holes are studied with localization. Perhaps we could discuss that later, although I'm not an expert. So the concrete evidence for our proposal will come entirely from the three-dimensional case. And the evidence is much less than a proof. It's based, I should have said mostly, from classical solutions in which ADS3 is replaced by what's called technically a hyperbolic 3 manifold. that just means a classical solution of Einstein's equations in 3 dimensions with appropriate conformal boundary. I put in the word mostly because there are some limited results about non-solutions which behave in the way I'll be telling you, the same as the solutions do. But mainly we'll be studying classical solutions. We'll show that the hyperbolic geometry works out in such a way that sub-threshold observables only receive contributions from connected manifolds. Well, if there really are observables that don't see any ensemble averaging, that strongly indicates that there's no ensemble averaging in examples of the duality derived from string/n theory. And I actually think this is also true for d equals 2. I've said d equal or greater than 3 to avoid some technical issues that we can discuss if you ask about later. Now, what we'll say is far from a proof, because it's based on studying a semi-classical expansion around a certain type of classical solution. Personally, I had a strong prior that there's no ensemble averaging because there's no ensemble. And the fact that you can identify observables not subject to any apparent ensemble averaging is further evidence in that direction. But this raises the question, why are any observables subject to apparent ensemble averaging? I'll make a proposal at the end of the talk. So the talk will have 2 parts. In the first part, I'll explain a class of observables where if you only look at those observables, you see no evidence for ensemble averaging from any calculation we know how to do. Then in the last part of the talk, I'll explain a proposal for what ensemble averaging means. For now, I'll just point out that this is something I didn't erase from last time. For now, I'll just point out that the observables that are subject to apparent ensemble averaging involve black hole states. So an explanation of why there appears to be ensemble averaging for anything will have to involve a difference between black hole states and subthreshold states, states that aren't black holes. So I'll say what I think the key differences are at the end of the talk. Actually, in this work, I started with that part of it. So originally I had the explanation or a proposed explanation of ensemble averaging for black hole states. But then it started to bother me that this explanation wouldn't make any sense for states that aren't black holes. So it had to be the case that if you look at the states that aren't black holes, you don't see any sign for ensemble averaging. So then I wanted to check that, but as you'll see, it involves statements about hyperbolic geometry, which were too hard to prove. So I ended up collaborating with a mathematician who works on hyperbolic geometry, Jean-Marc Schlenker, who I mentioned at the beginning of the talk. And we wrote a joint paper whose mathematical part consists of proving some statements of hyperbolic geometry, whose relevance I'll explain in a few moments. They go into justifying the statements that sub-threshold observables show no sign of ensemble averaging. So knowing that the states that aren't black holes show no sign of ensemble averaging means that you can explain apparent ensemble averaging using properties that only hold for black holes and not for the sub-threshold states. And that's what I'll do at the end of the talk. So any questions now?
Just a curiosity. If you consider statistical mechanics and you consider an almost integrable system, that is, that you don't not have as many charges as the dimension of a space, it's clear that you may have some observables which are not dependent on the average, since they depend only on the conserved charges, while there are other observables which depend on the average, since you do not fix all the degrees of freedom. So I was wondering whether it could be something similar here.
That's a very good question, but I actually think it isn't. You're asking about a system that has a lot of conserved charges, but not enough to be truly integrable.
Yes, this is the point.
We're in a different situation. So we have ADS5 times S5 with n units of flux. And there's integrability only for a large n and fixed energy. So there isn't exact integrability for anything. So there aren't any conserved quantity. There are no higher conserved quantities that are truly conserved. They're only conserved in the large n limit and only if you keep the energy fixed when you take the large n limit. Technically, they're conserved at the level of planar Feynman diagrams. And planar Feynman diagrams aren't everything, but they do describe the large n limit at fixed energies. And you can also make an infinitesimal perturbation around the large n limit. So if you keep the fixed energy and you expand in 1 over n. To all, well, what I'm about to say goes beyond what's been proved, but it's believed that to all orders in 1 over n, the integrability is still applicable. However, if you take n to be an exact integer, integrability is completely false. Of course, it can be, okay, for very low energies compared to n, it can be a good approximation. Well, I'm going to express things in a slightly different way, which will make it sound like what you've said is true. So perhaps I should not have said it wasn't. Imagine that n is 1,000,000 and the energy is 6. Then integrability is going to be a good approximation. Now imagine the energy is 1,000,000 and the energy is 100 million. Then integrability will be completely not applicable at all. So that way of describing it makes it sound somewhat like what you've explained.
Yes, okay. Thanks a lot.
Sure. Any other questions? So in anti-de Sitter space, that means with negative cosmological constant, there's a Hawking-Page transition. Above this transition, the typical state is a black hole. Below the transition, it is not. The sub-threshold states, the sub-threshold observables that I claim don't see ensemble averaging, are the ones that only involve sub-threshold states. That is, states below the black hole threshold. I think I've probably said that before. Since JT gravity in 2 dimensions is the example that was analyzed and described completely in terms of an ensemble average, perhaps it's worth mentioning that JT gravity does not have a black hole threshold. In that theory, in effect, all states are black holes. Anyway, let's discuss 3 dimensions. Even before ADS-CFT duality was understood in general, Brown and Henneaux discovered that in an ADS3-like universe, by which I mean simply a world, ADS3 is a little bit like a cylinder, except that, well, this isn't a systematic lecture on ADS, but the boundary of infinity is at spatial infinity, but it's also what's called conformal infinity. It's infinitely far away in space, but light signals from the bulk can reach there and back in finite time. And therefore, boundary conditions at spatial infinity can influence the bulk physics. And well, that last observation is kind of an elementary starting point that leads to the duality being possible. Anyway, an ADS3-like universe is a universe that near spatial infinity looks like ADS3, anti-de Sitter 3 space. In bulk, it might be more complicated. There might be a black hole, or who knows, any topology is possible in the bulk. What I'm trying to draw here is a hint of handles being attached to the bulk so that the bulk topology is more complicated. But at least near the boundary, an ADS3-like universe looks like a cylinder. The boundary is a 2-dimensional world. The boundary is R times a circle, where R is time and the circle is space. And then Brown and Henneaux showed that in this 2-dimensional world, you can define a stress tensor in terms of the asymptotic behavior of the gravitational field. So, well, their work could have been a starting point for the SCF2 duality. What actually happened was that after the duality was discovered in a different way, Strominger recognized that what Brown and Henneaux were saying was an example of the ADS-CFT duality, or a manifestation of it. There's much more to a CFT than just having a stress tensor. So, for example, Brown and Henneaux were considering pure gravity in ADS-CFT. And we actually today do not believe that there is a boundary CFT for pure gravity, only a stress tensor. But with the modern understanding, we believe there really is a 2D CFT. Okay, I got my thoughts out of order. In terms of Newton's constant G and the radius of curvature L, the Brown and Henneaux formula for the stress tensor, or central charge of the stress tensor, was that it's 3L over 2G. That formula has the important property that in the semi-classical region of gravity, G is very small compared to L, and therefore C is very large. So C plays the role of N in other examples of the duality. And in fact, in many ADS3 CFT examples, C is controlled by an integer N, or one or more integers N. So when I say large N, that's in 3 dimensions going to be the same thing as large C. Now, Brown and Henneaux showed they could define a stress tensor with this value of C. There's much more to a CFT than a stress tensor. But with the modern understanding, we believe that in examples of the duality derived from string/M theory, there really is a 2-dimensional CFT with this value of C on the boundary. Oh, okay, this is another place I might stop for questions, actually. Well, nobody's asking why we believe this, but one reason we believe it is that in many examples, we know what the CFT is. So that's one good answer. But it's important that you can here are considering an example of the duality derived from string/M theory. Those are the cases where in many instances, we know what the boundary CFT is, and in particular, we believe it exists. For pure gravity, which was actually the setting of Brown and Henneaux, there's no sign that there is a boundary CFT. Now, the ground state energy of a 2-dimensional CFT of central charge C is minus C over 12. So that, I'm calling that E0, the ground state energy. And with the Brown-Henneaux formula for C, that's minus L over 8G. For large beta, the partition function of anything is dominated by the ground state. So trace e to the minus beta h in this case grows exponentially because the ground state energy is negative. It grows exponentially as e to the beta L over 8G. So it has exponential growth for large beta, and the coefficient is very large in the semi-classical region of gravity, which is where G is small. How are we supposed to reproduce this exponential growth in gravity? Well, I've written the Einstein-Hilbert action. Well, I wrote it without the boundary terms for simplicity, although they'll be important in a way I mentioned in a second. It's important that there's a minus sign in Euclidean signature in front of the action. And the second term in the action is a multiple of the volume. It's a multiple of the volume with a negative coefficient because of that minus sign. But on shell R is minus 6 over L squared. So the R term is also a multiple of the volume, and it has a negative coefficient so that the action ends up being positive. So the Einstein action for a classical solution with large volume is large and positive. And that means that a classical solution with large volume will make an exponentially small contribution to a path integral. In ADS CFT, you're interested not in a manifold X without boundary, where this discussion here would be adequate. You're usually interested in a manifold X with a non-empty conformal boundary, as I keep describing. And since the boundary is really at spatial infinity, the volume of X in that case is actually infinite because it diverges near the boundary. Such an X always has an infinite volume. However, it's now important to include boundary counterterms, which include but are not only the Brown-York boundary term. After subtracting boundary counterterms, you can define a finite renormalized volume V sub r. And the renormalized action is not the volume, but the renormalized volume times the same constant as before. The way you define the renormalized volume is as follows. So if I put the boundary at rho equals 0, and so rho is non-negative, the metric of an asymptotically ADS manifold looks like this. Oh, sorry. GAB depends on both X and rho. X are the coordinates other than rho. The boundary is at rho equals 0. If you calculate the total volume using this, you'll find it's infinite. You define X epsilon by the condition that rho is equal to or greater than epsilon. And then you take the volume of X epsilon, but it diverges, so you have to subtract some counterterms. One is 1 over epsilon times the area, and another one is log epsilon times the Euler characteristic of the boundary. And then you take the limit of this as epsilon goes to 0. And all that is what I'm calling the renormalized volume of X. I may have gone through that a little bit too fast, but what I'm trying to say is simply, you cut off the volume by putting a cutoff at rho equals epsilon. The volume diverges, and you simply subtract the divergent terms. The divergent terms are local along the boundary, so it's physically sensible to subtract them. Subtracting the divergent terms means including some certain local boundary terms in the boundary action, in the action. So you find what the boundary terms in the action have to be so that the divergent part of the volume cancels. Any questions about that?
Sorry, just a request. Can you say a little bit more about the last term in this limit? It's log epsilon.
Well, the last term is simply the integral over m.
Over the boundary.
Okay. G times the curvature of the boundary. Optical invariant. It's a multiple of the Euler characteristic. But to be physically sensible, what's physically sensible to subtract are local integrals along the boundary.
I see. Yes.
You don't have to go very far into this before it's obvious that in any dimension, see, you have this metric. I'll describe it in a way that's true in any dimension, although it's simpler if the boundary is two-dimensional. The divergence comes from near rho equals 0, but the divergent part can only depend on derivatives of the metric with respect to rho up to some finite order. Because if you expand the metric in powers of rho up to a sufficiently high order, obviously everything will become convergent. The rho integral will become convergent. So anything that you get that only involves derivatives of the metric up to finite order is going to be an integral over the boundary of a local expression. And therefore, there's some local counterterm, which you could think of as coming from some boundary terms in the action, whose inclusion will cancel the divergent part of the volume of X of epsilon. So when the boundary is two-dimensional, the divergent terms are just the area and the Euler characteristic of M. Any other questions? No other questions? Now, the important thing about this is that to define the renormalized volume, we had to make a subtraction. Volumes are positive, but renormalized volumes, it turns out, are usually positive, but not always. And to get exponential growth, we need a negative renormalized volume, because the contribution of a manifold x to the path integral for small g is e to the minus the normalized volume over 4 pi g L squared. Of course, that multiplies a series of quantum corrections, but they won't affect the question of whether there's exponential growth with a large coefficient 1 over g. So anything that's going to give exponential growth has to have a negative normalized volume. So with this in mind, let's discuss how to recover the exponential growth of the partition function from gravity. Well, we have to reproduce it from the exponential of minus the renormalized volume, which means we need a negative value for the renormalized volume, which moreover has to be this. So the renormalized volume has to be not just negative, but proportional to beta. So it's large and negative for large beta, and it has to have the right coefficient. So what I've written here is the metric of the anti-de Sitter space. If I had a minus sign in front, this would be the Lorentz signature. With a plus sign, this is Euclidean signature. We could take t to be a real variable, but if we're trying to calculate a partition function, trace e to the minus beta h, then we want t to be a periodic variable of period beta. So if we do that, we get a manifold whose boundary is actually a torus. Its conformal boundary is a torus with the circumference beta in one direction and 2 pi in the other direction. And this manifold has precisely the necessary renormalized volume minus pi beta L cubed over 2. That statement is equivalent to the computation of the ADM mass of ADS3 in the original BTZ paper. They showed that the ADM mass was -1 in their units. It's equivalent, in the way I'm presenting it, to the statement that the renormalized volume is this. Now, in d equals 3, the threshold for black hole states is energy 0, as also shown in the original BTZ paper. So now let's consider a general state whose energy is minus e over 12, the ground state energy, plus some excitation energy that I'll call epsilon I. And so then we consider any state that's above the ground state by a finite amount as c becomes large. Such a state has an energy EI that's negative, it's large and negative, it's close to minus c over 12, above it only by finite amounts. So it'll make an exponentially growing contribution to the partition function. It doesn't grow quite as fast as the ground state contribution, but almost as fast. So all those things have got to come from manifolds with a large negative renormalized volume. So all exponential, and to state this in the opposite way from what I just said, what's written here is that all exponentially growing contributions to the partition function come from states of negative energy. Since the black hole threshold is at 0, the states of negative energy are what I'm calling subthreshold states. States above the black hole threshold have positive energy. The propagation of such a state through imaginary time beta gives an exponentially decaying factor, e to the minus beta e, not an exponentially growing factor. So we find subthreshold states by finding exponential growth, and black holes would instead give exponential decay. Now, what we want to do is to find an observable more. So I've explained one particular manifold, which is thermal ADS, that does have a negative renormalized volume. And moreover, its renormalized volume is large and negative when beta is large. You can look at all the classical solutions of Einstein's equations with a conformal boundary that's a torus. A torus is important because it will contribute to the partition function. And you can show that only thermal ADS has normalized volume of order a positive number times beta for beta to infinity. All other classical solutions have a normalized volume that goes to 0 as beta goes to infinity. That's the answer in genus 1. And that's, well, that classical fact was important in various papers 10 or even 20 years ago. So that was known long before the current project that I'm reporting today. If you like, what we did was to generalize that fact to higher genus and to interpret it in terms of my statement that certain observables. Okay. Okay. There's some tricky details about genus 1, which are the honest reason I want to go on to genus higher than 1. You can ask questions about genus 1 later, but if I tried to make more complete statements, we would run into some technicalities. So I'm going to go on to discuss more complicated observables in genus 2 and higher, which will be the real test of my claim about the subthreshold states. But maybe now is a good time to try to ask if there are more questions. So here I've drawn a genus 2 Riemann surface, and I've drawn 3 circles, A, B, and C, which have the property that they are non-intersecting and they're homologically independent. Now, there's an exact formula that you can write for Z of n as follows. You sum over the states, which I'll call little a, little b, and little c, that go through the circles I've drawn as big A, big B, and big C. So for example, little a you could think of as propagating in this way. The others propagate this way or this way. The direction of the arrow is meaningless. You could look at the picture from left to right or from right to left. But the state that's defined on this circle is propagating in the horizontal direction. The partition function can be written as a sum over all states. And then there's a factor. Well, to make it exactly the way I'll say, you should imagine that the metric around the circle A is not exactly the way I've drawn it. Think of it more as having a long tube with a length beta. So that the state little a is propagating for an imaginary time beta, and then it joins onto the rest of the surface. At the cost of messing up my picture, I'll try to draw it more that way. So here's the rest of the surface, but imagine this, think of this part as a long tube. Actually, people who work on string field theory will be very familiar with this, because in Zweibach's string field theory, basically Riemann surfaces are always constructed this way. You have a physical string state. Part of the Riemann surface is constructed as a flat tube that has a minimum length. And then the rest of it is unspecified or not specified in a simple way. So here, if the states have energies EA, EB, and EC, and propagate through imaginary times beta A, beta B, and beta C, we'll have a factor e to the minus beta A times EA, minus beta B times EB, minus beta C times EC. That's the factor you get because of propagation of the states through the tubes. But then you also have to do a path integral on the left and right. What do you see on the left and right? Well, I'm going to have to erase some of what I've drawn just so you can see it better, I think. To understand what you have on the left, and although again, people who are familiar with string field theory will be familiar with what I'm about to say, I hope. Imagine cutting the Riemann surface on these 3 circles. You're left with a 3-hole sphere on the left and a 3-hole sphere on the right. And the partition function on a 3-hole sphere, in general, I've drawn it, it's on my next slide, but sorry. I hate to go ahead to the next slide, so I'm going to give an ad hoc drawing. The partition function on a 3-hole sphere with boundary states I, J, and K computes a 3-point function, OI, OJ, OK. a 3-point function of the corresponding vertex operators that correspond to those states. I say it again in a little while in a slide. So here we have OA, OB, OB times OA, OC, OC in this particular example, because on the left, the 3 holes are labeled respectively by A, B, and B, on the right by A, C, and C. So this is an exact formula for the partition function as a sum over all possible states. So one of the most basic facts about quantum field theory is that you can write any amplitude in that way in terms of a complete sum over all possible intermediate states with various couplings. Now, if we look at the complete partition function, it's going to show apparent ensemble averaging. We're not going to look at the complete partition function. We're going to look at the part of Z of M that has exponential growth if any of beta A, beta B, or beta C go to infinity. So that means the partition function is keeping everything else fixed as a function of beta A, beta B, and beta C. But we're not going to study all of it. We're just going to study the pieces that are exponentially growing in all 3 limits. If you like, we throw away any piece that's bounded in any of the 3 limits and study what remains, the singular part. It's like studying the singular coefficients of a modular form near the cusp. Is the setup clear for what part of the partition function we're going to study?
Yes, I think it is.
Just a curiosity. So when you send beta to infinity from the string, if you were considering a string, this would be considering the low energy states of the infrared limit.
Yes, not only that that be true in string theory, but it's true for us. So the reason what you said is true is that when you take beta to infinity, you have a factor e to the minus beta times the energy. So the dominant contribution will be from the ground state, and all the exponentially growing contributions are from states of negative energy. We're going to look at not only the ground state, but all the exponentially growing contributions. Sorry, does that answer your question?
Yes, thanks.
Okay. Any other questions?
Just the Zm was introduced as a, so it involves the sum over all the geometries of the bulk. So over here, all the geometries are somehow taken care by.
No. Here we're not, on this slide, there's no duality. This is just a statement about 2-dimensional CFT. This is an exact statement about any 2-dimensional CFT, whether or not it participates in the duality.
I see. It's okay. It's the CFT just living on the boundary. It has nothing to do with the.
Yes. In general, in quantum theory, anything can be computed by summing over intermediate states. In elementary quantum mechanics, you have a world line. You cut it at any point and sum over states. Usually the world line is parameterized by time. In quantum field theory, you can cut in multiple places simultaneously because the topology is more complicated. But wherever you've cut, if you cut and sum over all possible intermediate states, you reproduce the complete answer. You could think of that, depending on your point of view about quantum field theory, that's either part of the axioms or else it's a theorem or something. But it's one of the most fundamental statements about quantum field theory. So here I've just made an exact statement about quantum field theory in general. Then we'll discuss interpreting it in terms of the bulk.
Great.
Any other
Thank you.
questions?
I have a short question. If you have different sort of sectors with different temperatures here, is there a meaningful sense of equilibrium, or do they talk to each other?
Well, temperature and equilibrium aren't really very well-defined concepts here. We have a conventional field theory that can be defined on a manifold of any metric It's conformally invariant, so we only care about the conformal structure, not the detailed metric. And it's up to me what metric I want to pick. So the metric, in general, we could be anywhere in the moduli space of conformal structures on M. I'm just telling you that I've picked 3 circles, and now I want to pick 3 of the real moduli, beta A, beta B, and beta C, to be large, and study the behavior when those 3 moduli become large. We could do something else. In general, we could specify the moduli to be whatever we want. But this is what is useful here for a reason you'll see in a second. Any other questions? Well, I'm actually here introducing some language. So in the last discussion, I talked about this tube being very large. But that's one language. A different language is to take this very small. If this has a size R, then the only conformal invariant is beta over R. So beta to infinity is equivalent to R going to 0. And hyperbolic geometers prefer to think in terms of R going to 0. So they say the cycle A is being pinched, by which they mean that the circle R is becoming very small. So it doesn't matter conformally if we take beta large or R small. That's another fact that should be familiar to people who do string field theory, or any kind of string theory, really. So in the limit that the cycle A is pinched, the CFT partition function grows exponentially by that factor that we discussed, which was e to the minus beta A times the energy of the state passing through the cycle A, which can be negative. How would we reproduce that from gravity? To reproduce it from gravity, we need a 3-manifold X whose renormalized volume goes to minus infinity when A is pinched. But that won't be sufficient to give us a contribution to the amplitude that is free of ensemble averaging. The reason is that when, even if the state passing through A, let's say that the passing through A is not a black hole, the other guys could be black holes. So in that situation, we'd be studying the coupling of a non-black hole passing through A to black holes passing through B or C. And if anything involves black holes, I don't claim it doesn't show signs of ensemble averaging. So just having a renormalized volume that goes to minus infinity when A is pinched will not be enough to give an amplitude that doesn't show ensemble averaging. And we need to be more precise if we want to get an amplitude that doesn't show ensemble averaging. Suppose that X is such that the renormalized volume goes to minus infinity when any of A, B, or C is pinched. That means that X is contributing to an amplitude in which A, B, and C are all subthresholds. In other words, if the renormalized volume is going to minus infinity when any of A, B, or C is pinched, that means that X is going to give a contribution with exponential growth in any of the 3 pinching limits. And that means that it makes a contribution where the states propagating through any of A, B, or C is a subthreshold state. Well, that's the situation which is not supposed to show ensemble averaging, because then there's a contribution where as I explained already, if you cut on A, B, and C, you get a 3-hole sphere on the left and a 3-hole sphere on the right. And you get a contribution which involves the propagation and energy of the 3 states, and also one that involves the couplings on the left and on the right. If the states are subthreshold states, this coupling is one of the observables that I'm claiming is not supposed to show ensemble averaging. So here, OI, OJ, and OK are vertex operators corresponding to the three states. OI, OJ, OK is a 3-point function on a sphere. According to our basic hypothesis, the energies, spins, and trilinear couplings of the subthreshold states are not affected by ensemble averaging. To state a prediction for hyperbolic geometry, that means that if M is a component of the conformal boundary of X, and the normalized volume goes to -infinity when any of A, B, or C is pinched, then the conformal boundary of X should be connected and should only consist of M. This is the key statement, so I hope I've managed to state it clearly. If VR is going to -infinity when any of A, B, or C is pinched, that means that X is contributing to a subthreshold amplitude, an amplitude that can be expressed only in terms of subthreshold states, say A, B, and C, and their couplings, and such. So the piece of the partition function that grows exponentially in all three channels is supposed to not show any ensemble averaging. And that means that a 3 manifold that contributes to it should only have a connected boundary, not a disconnected one, which would be a sign of ensemble averaging, a sign of a connected correlator with something else. So this is the basic prediction that if X is such that its renormalized volume goes to -infinity in any of the three limits, then its conformal boundary should only be M, no other pieces. So that's a special case of what was proved in the paper, in the mathematical appendix that is 99% due to my co-author, Jean-Marc Schlenker, of our paper. So actually, we proved more. It turns out there are infinitely many X's that have M in its conformal boundary, but there's only one X that has the property that the normalized volume goes to -infinity in any of the three pinching limits. And the only X that has that property is the one suggested by the picture. In other words, this picture suggests an embedding of that Riemann surface in R3. If you do take that embedding in R3, the interior with that embedding is a manifold X whose boundary is M. And X admits a hyperbolic metric, that is a solution of Einstein's equations. And it turns out that this is the only X whose renormalized volume goes to -infinity in the three pinching limits. We would like the statement to have a genus G generalization for every G. So if a genus G surface is cut along 3G minus 3 independent circles S alpha, as sorry, as drawn here for G equals 3, it decomposes into a union of 2G minus 2 3-hole spheres. If the renormalized volume goes to -infinity whenever any of the S alpha is pinched, then the boundary of X should be connected and consist only of M. So again, we proved that for all J, and we proved a stronger statement that wasn't really needed, which is that there's a unique X that has the property that VR goes to -infinity in each of the 3G minus 3 limits. It's, again, the X suggested by this picture. It's the interior when M is embedded in R3 in the way that the picture suggests. If you know your Riemann surfaces, then you know that we could make a mapping class transformation. This is something that, again, people in string field theory or any kind of string theory would probably know well. You can make a mapping class transformation that would exchange these 3G minus 3 circles with some others. And with that other set of circles, what would go with it would be a different picture that would suggest a different embedding in R3 and a different X. And those aren't all the possible X's. There are many, many X's that have conformal boundary M and solutions of Einstein's equations. Infinitely many that come by what I just said and infinitely many others. But of all of those, the only one where VR goes to -infinity in each of the 3G minus 3 limits is the one suggested by the picture. And in particular, its conformal boundary is M, which means it doesn't contribute any apparent ensemble averaging, for the subthreshold observables. In other words, for the part of the partition function that grows exponentially in each of the limits. So the mathematical part of my paper with Jean-Marc Schlenker consisted of proving two statements that tell us exactly when which x's are relevant. So one says that there's exponential growth in a pinching limit if and only if the cycle which is pinched is the boundary of a disk inside. And the second statement says that if there are a lot of cycles that are boundaries of disks, then the boundary is connected and consists only of n. And moreover, X is a Schottky manifold, which is a fancy way to say that it's the manifold suggested by the picture. So what I said here, that there's unique X, which is the one suggested by the picture, is the important case for our applications. But on this slide, I have a more complete statement of what was proved in the paper. Although not quite complete, what was proved in the paper is slightly more precise than I wrote here. I think I'm going to skip the part of the talk, the slides, since I've already gone on for more than an hour and I haven't gotten to the second part of the talk. I think I'm going to skip the summary, the more detailed explanation of what was proved mathematically in the paper. I'll say that in the paper, there is a section 3 that has a qualitative summary for physicists. And there's also an appendix, 99% written by my co-author, with detailed mathematical proofs. So I think I won't say any more about the mathematical statements or the proofs unless someone wants to ask a question. And instead, I'm going to go on and discuss a simple example.
Yeah, actually, I do have just a short question. What are the constraints on a manifold? Like, does it matter what kind it's going to be?
Well, we're interested in manifolds that have solutions of Einstein's equations with negative cosmological constant. People who study hyperbolic geometry know that that's a very weak constraint. So, well, it's a little funny because some of the most 3 manifolds have that property, but some of the most elementary ones that you would think of first do not. So for a normal person, they seem like exotic 3 manifolds, but to a specialist on 3 manifolds, they seem like almost any 3 manifold. Anyway, the answer is that the X is allowed to be anything that admits a classical solution of Einstein's equations. You could ask me if we should consider X's that aren't classical solutions, and that's interesting. But for the mathematical statements in the paper, we consider classical solutions.
Okay, thank you.
Sure. Any other questions? If there aren't more questions, I won't say more about the mathematical statements, and instead I'm going to illustrate them with an example. This is an example, it's an elementary example that I was quite familiar with, and I was also familiar with the Genus 1 statements. So we generalize what was true for Genus 1 and also what's true in this example. And it was because knowing those examples was part of why I thought it might be true in general, and therefore look for a math collaborator to help prove it in general. So the example is what's called a Fuchsian manifold. That's topologically the product of Riemann surface times R, where M is a Riemann surface of genus equal to or bigger than 2. Then it admits metrics of constant negative curvature. And then a simple example of what we've been talking about in this lecture, solutions of Einstein's equations with disconnected boundary, is this thing. That's an exact solution of Einstein's equations in 3 dimensions, given that d omega squared was a solution in 2 dimensions. The conformal boundary consists of 2 copies. The picture looks a little bit like this. It's hard to draw properly because the boundary is at infinity. But it gets bigger at the ends if t is large because the cosh blows up as t goes to infinity. It's smaller in the interior. It's a little bit like what I've drawn, except that it's infinitely big at the 2 ends. So the ends are infinitely far away. That's always true in asymptotically anti-de Sitter space. And the conformal boundary consists of 2 copies. at minus infinity and plus infinity in T. So they have the same metric, so they have the same or opposite complex structures. Now, no cycle in either one bounds a disk in X. So in view of what we proved, the renormalized volume will never go to minus infinity. But in this example, that's easy to check. So I just stated things out of order. This is such an easy calculation that it was quite familiar and suggested what might be the general pattern. For this particular example, you can easily calculate the renormalized volume following the recipe I gave before, and you'll find that the renormalized volume is a topological invariant, meaning it doesn't depend on which r equals -2 metric we picked. It only depends on the genus of sigma, or m rather, I've been calling it, not on the particular metric of r equals -2. So in other words, VR only depends on the Euler characteristic of m. So it's a topological invariant, so it never goes to minus infinity. So we never see subthreshold states if we rely on this type of solution of Einstein's equations. However, there's a flaw. The trouble with this example is that for the explicit metric, we can't independently vary the complex structures in ML and MR. They're the same. So we can pinch on both sides, but we don't know what happens if we pinch on one side, leaving the other one fixed. So I wanted to know what happens if you pinch one and not the other. There's an existence proof that says that more general hyperbolic metrics exist with independent complex structures on the two sides. So you can pinch one without pinching the other. But although there's an existence proof for that metric, I don't know how to visualize what it looks like. And there certainly is no explicit formula for it. So to know that the renormalized volume doesn't go to minus infinity in that limit needs a better argument. And that's given in the appendix of our paper using properties of the Weil-Petersson metric on moduli space and of the stress tensor of the CFT. So the manifold M times R and others with disconnected boundaries only contributes to amplitudes involving black hole states, never to amplitudes that can be expressed solely in terms of energy, spins, and couplings of states that aren't black holes. So that's what I have to say by way of evidence that sub-threshold amplitudes show no sign of ensemble averaging. Together with the fact that anyway there isn't a suitable ensemble, this strongly suggests that in ADS CFT for D of at least 3, we're not really seeing an ensemble average. But if that's the case, why do amplitudes that involve black hole states show signs of ensemble averaging? Clearly, we need an explanation that involves a difference between subthreshold states and black hole states. So in the last part of the talk, I'm going to go on to tell you what I think ensemble averaging means for black holes. I want to suggest that these two facts are the key differences. The first fact is that black hole physics is highly chaotic, as shown by Schenker and Stanford. The second fact is that energies and couplings of black hole states don't have a large n limit. The first point about chaos is well established. The assertion that energies and couplings of black hole states don't have a large n limit may seem less obvious or less familiar. But I think you might become convinced of it if you just ask yourself, in what sense could we hope for such a limit? The entropy, say at fixed temperature, grows as a power of n. So the Hilbert space if n is 10 to the 6 plus 1 is much bigger than the Hilbert space at n equals 10 to the 6. Almost all states are new. For example, in n equals 4, in d equals 4, the entropy is of order n squared. So the dimension of the Hilbert space at n is roughly e to the n squared. So we'd be comparing e to the 10 to the 12 plus 2 times 10 to the 6 plus 1 e to the 10 to the 12. The ratio of the two is e to the 2 times 10 to the 6 plus 1. That's a stupendously big number, of course. So almost all states in the black hole Hilbert space at a given value of n don't have any antecedents for n minus 1. They're all new. So it's hard to imagine a sense in which you could say, hope to say that the black hole spectrum has a large n limit. And no one has suggested such a statement in the literature. So no such claim has ever been made, and it's hard to imagine what the claim could be. So I'm simply going to say that there's no surprises here. There have been no such claims, and there will be none. In the somewhat analogous case of the large volume limit of quantum statistical mechanics, the accepted answer is that the Hilbert space does not have a large V limit. That's actually why the thermofield double state was introduced in rigorous approaches to quantum statistical mechanics. It does have a large V limit. Likewise, in the case of a black hole, the thermofield double entangled state of two black holes has a large n limit. But there's no reason to think, and it's hard to imagine what it could be, that for a single black hole, you would have a large n limit. When you, I'm not sure that what I said here is going to be familiar to everybody, even though it's elementary. When you learned quantum statistical mechanics, what probably happened was your textbook considered some simple system like an ideal gas in finite volume, computed the partition function and the thermodynamic functions, and maybe some thermal correlation functions if you were more sophisticated. Then it showed they had a large volume limit. So you learned that the entropy, energy, and thermal correlation functions have thermodynamic limits. Your textbook didn't say that the Hilbert space in which they were computed doesn't have a large volume limit, but it also didn't claim that there was a large volume limit. And if you think a little bit, you'll get discouraged about a large volume limit, because a typical space state in infinite volume at non-zero temperature would have an uncountable dimension with independent excitations in all regions of space. But normally in physics, you do physics in a countable Hilbert space, or what's called a separable Hilbert space with countable dimension. It's not normally useful in physics to introduce a non-separable Hilbert space. So anyway, there's no standard claim for a large volume limit of the Hilbert space of quantum statistical mechanics, and I'm simply saying that the Hilbert space of ADS-CFT at large n is similar. So I'm simply saying that there's no reason to think there's any unknown sense in which the black hole Hilbert space has a large n limit. When I say the black hole energies and couplings don't have a large n limit, the statement is open-ended because there's no proposed sense in which they could have a limit. And it's hard to imagine such a sense because of the way the Hilbert space is growing. But anyway, what I really mean is meant to be open-ended. The statement is really that there's no regularity in the microstructure of black hole physics for large n beyond what is known. Well, what's known? What's known is that the entropy and other averages over the spectrum are smooth functions of energy, spin, and n, and perhaps other couplings when there are other couplings. And that certain average functions of couplings, this isn't meant to be summed over ij and k. Certain average functions of coupling, such as the average value of lambda ij k squared, average, not summed, over nearby states of nearby energy, are likewise smooth functions of the energy, spins, and n. So these averages have been studied originally by Cardy, Maloney, and Maxfield, and later by other authors. Not everything about them that could be said has been said, and most of the literature deals with abstract CFTs rather than CFTs that have gravitational duals. I think you can say a little bit more if you know that there's a gravitational dual. But regardless, in spirit, what I'm considered to be known about the large n limit is that there's regular behavior for thermodynamic functions, including thermal excitation values and correlation functions. And also, although not everything that can and will be done about it has been done, that as initiated by these authors, certain average functions of couplings are likewise smooth functions. So there's a lot of regularity that is known about the large n limit. The assertion that the black hole energies and couplings don't have a large n limit means that the regularity which is known is representative of what there is. That we shouldn't expect to discover something of a completely different nature that's regular for large n. Now, assuming this, let's consider any observable curly W that only depends on the Hamiltonian Hn of the black hole states. The most important observable is the partition function for sufficiently small real beta, but we can consider any W. And I think it's a little clearer if we consider an arbitrary W. Chaos in black hole physics means that as far as any simple measurement is concerned, Hn can't be distinguished from a random matrix. A random matrix drawn from an ensemble that's determined by the thermodynamic functions. The entropy is a function of energy, spin, and other charges, if there are any. And n. Well, I said Hn, so n was specified. Now, Hn is completely non-random. As I said, it's believed there's no ensemble. So, for example, in n equals 4 Yang-Mills, there's a unique theory. Well, it actually depends in that case on the talent parameter, but there's an almost unique theory. If you specify the coupling, it becomes unique. And then Hn is a completely non-random matrix, a unique one determined by the axioms of SFT together with the symmetries. But in simple measurements, like measuring the partition function, you can't distinguish it from a random matrix. That's what the term pseudo-random means. A pseudo-random matrix is one that's very, very difficult to distinguish from a matrix that's truly random. If the spectrum has no regularity for large n beyond thermodynamics, this suggests that the Hn for different n are independent draws from a random matrix ensemble. In other words, Hn for each n is totally non-random, but chaos means it's pseudo-random. However, if we had a large n limit in some sense, that would mean that there was a limiting pseudo-random matrix for a large n that was controlling everything. Saying that the spectrum has no large n limit suggests that the Hn for different but large n should be thought of as independent pseudo-random matrices. And that's the hypothesis that I will discuss in the last 10 minutes. There are two important qualifications. One is the ensemble itself depends non-trivially but smoothly on n, since the entropy is a smooth function of n. Secondly, I'll argue at the end that the Hn for different n are only exponentially close to being statistically independent. And that might lead to departures from random matrix behavior. But it's easier to explain the argument if we assume first that the Hn are truly independent pseudo-random matrices. If the Hn are independent pseudo-random matrices, then an observable that depends only on Hn will be a smooth function of n only if it's self-averaging in random matrix theory, meaning it has almost the same value for almost any draw from the random matrix ensemble. The only reason random matrix theory is useful, or at least the main reason it's useful, is that there are a lot of self-averaging observables. So a lot of things about a chaotic system can be predicted from random matrix theory just because there are a lot of observables that are almost the same for any pseudo-random matrix drawn from the same ensemble. Those are called self-averaging observables. For example, the partition function is believed to be self-averaging for sufficiently small real beta, but if we give beta a sufficiently large imaginary part, it's believed to be no longer self-averaging. Now, imagine you're computing with a method that only is going to compute smooth functions of n. So maybe I should have said here presently known methods for the gravitational path integral, because localization could potentially compute non-smooth functions of n, although I'm not sure if there are any known examples where it does. I actually want to discuss that point with people who know more about localization than I do, or at least know more about some of the modern examples of localization than I do. But I don't know. But at least with the gravitational path integral, where we sum over finitely many critical points, we're always computing a smooth function of n. Anyway, if you have a method that can only compute smooth functions of n, it won't be able to calculate everything because some observables are not smooth functions of n. An observable that's not self-averaging in random matrix theory will not be a smooth function of n, because for every n, you'll be seeing a different pseudo-random matrix. And by definition, an observable that's not self-averaging will have completely different values at n of 10 to the 6 or n of 10 to the 6 plus 1. If it's not self-averaging, it will have a totally chaotic or totally erratic behavior as a function of n, and you won't be able to calculate it with a method that only calculates smooth functions of n. There's no crime there. The methods we have do not suffice to calculate everything. I'm just saying that methods that only calculate smooth functions of n, at best, will only be able to calculate functions that are self-averaging in random matrix theory. Now, the gravitational path integral summed over many critical points is an example of a method that only computes smooth functions of n. So therefore, the gravitational path integral will only compute things that are self-averaging in random matrix theory, and what it computes will look like a random matrix average. So, sorry for the phone in the background. So I claim that that's the basic reason that the gravitational path integral gives certain results that look like they come from random matrix theory. When you're doing black hole physics, only observables that are self-averaging in random matrix theory are smooth in n, and only such observables can be computed with the standard approach to the gravitational path integral. So the gravitational path integral will always give something that looks like it could have come from a random matrix theory. There isn't anything in that explanation beyond the assertion that black hole physics is chaotic and has no large n limit. And I claim that's the reason for apparent ensemble averaging in black hole physics. A statement I'll elaborate on now a little bit more. Even if W is not self-averaging in random matrix theory, it may have a non-zero random matrix average. And in that case, presently known methods might suffice to compute a smooth function of n that would really be only an average value of W averaged over nearby values of n. So there are observables that aren't self-averaging, but they do have averages. In such a case, you might be able to compute these observables by methods that only give smooth functions, but the smooth function won't really be giving you a good approximation to W at given n. What it will be giving you is an average over nearby values of n. So an example is the partition function with complex beta. Or well, a better example is the absolute value squared of that, where beta is complex. And beta 1 is large. This is an example. Saad, Schenker, and Stanford showed that it has an average in random matrix theory, but it's not self-averaging. It has an average in random matrix theory, but it also has large fluctuations around the average. So you could potentially calculate this by the gravitational path integral. You'll get a smooth function of n. That's not the correct answer. The correct answer has wild fluctuations when you change from n from 10 to the 6 to 10 to the 6 plus 1. But since there is a smooth average, a hypothesis is that what the gravitational path integral gives you is an average that's an average over wild fluctuations. I hope I didn't cause too much confusion with that explanation. More generally, you could consider k functions W1 up to Wk that only depend on the Hamiltonian. Whether or not they are individually self-averaging or have non-zero averages, their connected correlation function might have a non-zero average in random matrix theory. If it does, you might be able to calculate a smooth function of n that would be an average answer for this product of observables, the connected part. So a method that only gives smooth answers might suffice to compute a smooth function of n that would be an averaged value of this correlator, averaged over nearby values of n. These general considerations don't tell us how we're supposed to do the calculation. But let's specialize to the case that the w's are partition functions. So a partition function would be computed by a path integral in the boundary theory on a product of a sphere times a circle. The reason for a sphere is that, well, I should have said that Hn was meant to be, okay. The ground state of the CFT is a state on the sphere, and the low-lying states are states on a sphere. So the usual Hamiltonian of the CFT is the Hamiltonian on a sphere, and therefore the path integral, the partition function will be a path integral on a circle times a sphere. So suppose that each of our k observables, or n observables, is a partition function. The obvious hypothesis is that to calculate the connected correlator of a product of k partition functions, we should do a calculation by summing over manifolds X whose conformal boundary is a disjoint union of k copies of S1 times a sphere, where the circumference of the circle in the rth copy is the corresponding inverse temperature beta r. So the picture is hard to draw, but I'm drawing it as if little d minus 1 is 1. If there are 3 of these, you would sum over bulk manifolds whose boundary is a product of k copies of S1 times SD minus 2, something that looks like this. So that's the obvious hypothesis for how you'd be calculating these observables. The evidence for it is only that assuming because black hole physics is chaotic and assuming black hole physics has no large n limit, an average of such a product is the most general thing you might be able to calculate by a method that only gives smooth answers. And we notice that for the gravitational path integral, the methods of calculation are in one-to-one correspondence with the possible answers. So given everything we know about gravity, the obvious hypothesis is to match them, and that these methods of calculation give these answers. Any questions on any of that? So the proposal is that this is the meaning of connected amplitudes with disconnected boundary for the case that the boundaries have this particular topology. Now, I started with that topology because it corresponded to the exceptional case that we only need to know the Hamiltonians of the states and not the couplings, not the trilinear couplings or other information about the CFT. That enabled me to discuss it in terms of random matrix theory rather than random CFT. With more general boundary manifolds, we have to talk about pseudo-random CFTs, not just pseudo-random matrices. Here, we're not on such solid ground. But I can tell you what seems like the only or most plausible explanation. The couplings lambda ijk of black hole states are constrained by suitable crossing relations they satisfy. If you want to satisfy the crossing relations and all other CFT axioms exactly, it's believed there's no appropriate ensemble from which they can be drawn. In other words, as I said at the beginning, it's believed that all the possible parameters are known in an exact solution of the axioms. And there aren't enough to account for ensemble averaging. But if we're just discussing asymptotic expansions for large n, it's plausible there's a large ensemble of asymptotic solutions of the crossing relations. So that would be analogous to the fact that suppose you're interested in a relativistic S matrix. You'd like it to be unitary and physically sensible, and they're hard to come by. Above 2 dimensions, there aren't any exact, non-free, relativistic unitary S matrices. Only existence proofs for some supernormalizable theories in 3 dimensions. So exact ones are scarce and correspond to QFTs that are ultraviolet complete. But if you're willing to have not an exact one, but just a relativistic S matrix that makes sense order by order in expansion and powers of the energy, then in low energy effective field theory, there's an abundance of unitary S matrices. There's a vast swampland parameterized by the coefficients of all possible local operators in the effective action, with some mild restrictions, of relativistic S matrices that make sense to all orders in a low energy expansion. So I'm making an analogy where the energy in the S matrix corresponds to 1 over n, and the S matrix corresponds to a CFT. And there's a swampland of approximate S matrices that make sense for small energy. And I'm proposing there's a swampland of CFTs that make sense near n equals infinity, even to exponential accuracy near n equals infinity, but not exactly. So the proposal is that the CFT that governs black hole states for particular values of n looks like a pseudo-random draw from a vast swampland of effective CFTs that satisfy all crossing relations in an asymptotic sense for large n, but not exactly. For nearby but different values of n, we get almost independent pseudo-random CFTs. So observables that are sensitive to the black hole spectrum are smooth functions of n only to the extent that they are self-averaging quantities in random CFT. If we use a method, instead of writing we can only compute, I wish I'd written, if we use a method that can only compute quantities that have non-zero averages in random CFT, well, sorry, what I should have written is fine. If we use a method that only computes smooth functions of n, then we're only going to be able to compute quantities that have non-zero average in random CFTs. And what we compute will be smooth functions of n that are smooth approximations to the observables of interest. So going back to the question with which we started, when we compute what appears to be a connected correlator between k different partition functions by summing over connected manifolds X, which have k components in their boundary, what we're getting is a smooth function of n that's really an averaged value of the product of partition functions, averaged over nearby values of n. A short summary is ensemble averaging is really averaging over nearby values of n to get a smooth function of n. There's one more thing I want to explain, which was the statement that theories with different but nearby values of n are only exponentially close to being statistically independent, rather than being truly statistically independent. That's because in known examples, the theories at different n are unified in string/m theory and are connected by domain walls. So considering an amplitude with a wrapped brane that causes a jump in n between two boundary components. So here is m, here's m prime. I have n for m and n plus 1 for n prime. That happens because there's a wrapped brane in the interior shown by this red. So now X has two boundaries, but it also has a brane in the interior that causes a jump in the flux and therefore a jump in n. Well, such a thing will compute a connected correlation function between partition functions with different values of n. But it's going to be small because of the brane action. So because of the brane action, this will be smaller even than a connected correlator without the brane. So that's why I say that the theories with different values of n are extremely close to being statistically independent, but not truly statistically independent. So because they only are extremely close to being statistically independent, I think it's conceivable that more careful study of the black hole partition function, I think more careful study of the gravitational path integral, including brane contributions, might eventually show departures from random matrix predictions. So gravitational path integral comes very close to reproducing predictions of random matrix theory. That was discovered by people like Saad, Shanker, and Stanford, and motivated the whole discussion of ensemble averaging. But I actually think it's quite possible that more careful study will show that brane contributions give departures from random matrix theory. To summarize, today I've given evidence that energies and couplings of states below the black hole threshold are not affected by ensemble averaging, and I've proposed an interpretation of apparent ensemble averaging in the case of black hole states. Thanks for your attention.
Okay, thank you very much for the very thorough talk. We have, of course, space for questions now. Let me see if are there questions. I see people raising hands and clapping, but I don't really see the difference. Ivo, do you have a question?
Yes, I do,
okay.
indeed. Yeah. Yeah. So I was wondering whether these quasi-normal modes are another instance of what you were saying. Maybe I'm comparing apples with pears, but you know how when you compute these quasi-normal modes on the CFT side, if you're at finite end in ADS3, it's like a finite length string, and you have always have quasi-periodicity in that case. Whereas on the gravity side, at the moment you have a horizon, you have exponential decay, which gives this quasi-normal mode. So there's always been some sort of mismatch at any finite end between quasi-normal modes in the CFT and the actual exponential decay in gravity. So to me, it seems it's like a manifestation of this non-regularity of the spectrum at large n, but I'm not sure it's the same kind of.
I don't know if it's a good analogy or not. It might be. It's an interesting point. It involves things I don't know much about, I'm afraid.
Mm.
I can't comment usefully.
All right. Okay. Thank you.
Sure.
Do we have more questions?
So you're kind of doing a Fermi's golden rule, it seems to me. No, it's like quasi-continuous spectrum. You get some things right, but other things perhaps you don't, it seems to me.
So the string oscillating in ADS has real energies.
Mm-hmm.
That was your first point. Well, so it has real, it can still decay by it will still emit radiation, I assume, which will be quanta in ADS, and it will jump down to a less excited string.
But it would be reflected perhaps on the boundary of ADS, and then.
Well, if you start with only a string in ADS and let it oscillate for a long time, the string will shrink and you'll have all kinds of quanta in ADS. Eventually, the state will thermalize. If the energy is low enough, it won't form a black hole, but it will still thermalize over very long times. We're definitely getting into things I don't know much about, so I won't be able to say anything useful.
Yeah.
May I ask a very naive question?
Yes.
How do you include brane contributions in the gravitational path integral?
You literally include them. Well, gravitational path integral. From a low energy point of view, you just say that there's a brane that its world volume is a submanifold of space-time with certain dimension, and it carries certain fields, and there's a formula for its action. So there's standard formulas for the action of the brane in supergravity. So you literally just do a path integral. Well, instead of just metrics, you have metrics and possibly branes.
I see.
What I was saying here was that here I think we're actually getting some benefit from knowing that the examples, well, I think we're actually learning something from the fact that the theories with different n are all unified. All come from the same construction of string/n theory. It means that we can make domain walls between the different theories, and they're not truly statistically independent. If we had, well, okay. I actually think it's an interesting prediction that there are departures from random matrix theory.
Yes, definitely.
Yeah, are there more questions? If not, I would like to thank Witten again very much for giving the talk here today, and especially for having accepted in such a short notice.
Oh, well, thanks very much for the invitation, and thanks for all the questions, and be well, everybody. Good luck.
Yeah, thank you. Okay, bye-bye.